Good morning. I'm going to talk about graph algorithms on future architectures. Graphs are important and they're pervasive. Heterogeneous hardware is here, and we're building a library that helps developers use both of them. And the research is how can you tease apart the concerns between graph analysis and different kinds of hardware architectures. So it's funny, I put this slide in here because sometimes when I talk about graph analysis, I have to convince the audience that it's important and pervasive. Except that in each of the talks this morning that preceded me, somebody mentioned they were doing some kind of graph analysis. Graphs are used to represent computer networks, road networks. We heard about malware distribution networks earlier today and social networks. That bottom right one is an interesting one. That represents conflicts between editors of Wikipedia pages about the Cyprus dispute. You can use graphs to represent that and understand that and reason about it. And so just a reminder for everybody, when I'm talking about graphs, I'm talking about the mathematical concept of nodes and edges. You have nodes which are connected by edges. This is a very small graph. We're interested in larger graphs. Some of our customers are interested in graphs with billions of nodes and hundreds of billions of edges. And those edges can be weighted. And there are many different ways to represent graphs. Up top you see an adjacency list, which is a list of the nodes that a particular node is connected to in this directed graph. And on the bottom you see an adjacency matrix, which is a big array, which has an X in the spot if one node is connected to another one. And this affects how the programmer actually interacts with the graph and does graph analysis. In one case you might be doing object-oriented programming, looking at from nodes to nodes to nodes. In another case, for example, in the matrix, you might be doing linear algebra. And I'll talk a little bit about that moving forward. So it's important, it's pervasive, but it's also difficult. So graphs are notoriously difficult to parallelize. There's a small computation to communication ratio, and there's an unpredictability of data access. So if you're doing programming where you have very flat data or tabular data, you can kind of line that data up. You can go from your disk to your main memory to your cache to your processor. You can line that up and so that the computer knows what data it's going to access. Graphs, by their very nature, are not like that. You have a node connected to another node. It appears to be random. And so the time is, there's a lot of communication that happens. There's a National Research Council report that talked about this, the challenge of primitives. Develop a middleware for large-scale graph analysis. And you can say, they call it to provide a framework to express concisely a broad scope of computations, allow programming at the appropriate level of abstraction, and they're applicable in a wide range of problems. They also mentioned that the Graph 500 might be useful in this effort, and I'm going to talk about the Graph 500 because we use it extensively. Okay, so hopefully I've convinced you that graphs are important and pervasive, and now I'm going to talk about heterogeneous hardware. So heterogeneous hardware is here. If you look at the bottom left, you see a new phone. The Apple's A8 processor is a multi-core CPU. It has multi-core GPUs and a special purpose motion processor. And this is the phone that's in many people's pocket. Herb Sutter from Microsoft Research has been talking about the role of changing hardware for years and years. And 10 years ago, he wrote a paper called The Free Lunch is Over. And the free lunch that he was talking about was the increasing performance of computers just by the speed of processors. Because of Moore's law, you get more and more transistors. In the past, chip manufacturers used that to make chips faster. We hit a wall last decade. We still have all of those transistors, so what chip manufacturers end up doing is put more cores on the chip. And so developers now, to take advantage of those chips, they have to do multi-core or multi-threaded programming. Then just a few years ago, Herb Sutter wrote another paper called Welcome to the Jungle. And he had basically, in this paper, he said, well, the transition to parallel computation is complete. Everyone has a parallel computer everywhere now. But now we're in this jungle of cloud core and heterogeneous core. Not only do we have CPUs, we have GPUs, we have FPGAs. We heard about tile processors yesterday, all sorts of different kinds of processors. And then at the top, hopefully some of you are familiar with the top 500 list. This is kind of the benchmark for the fastest supercomputers in the world. And the top player in that list is a GPU machine, full of GPUs. And partially because of that, we decided with this research to focus on the GPU as the computational element, as that heterogeneous hardware that we're going to use for our graph analytics. We're not the only ones who say this. Another National Research Council report came out and talks about the future growth in computing performance will have to come from software parallelism that exploits hardware parallelism. We have to be able to bring libraries and things to developers so that they can take advantage of this new kind of hardware architecture. Simplifying the task of parallel programming requires software abstractions that provide powerful mechanisms to hide the underlying details. It's very important that developers can use high-level libraries and frameworks to do their work. So graph analysis is important and pervasive. We've got heterogeneous hardware, and I'll talk about the library that helps developers use both. So there's a couple of different concepts here. As Matt alluded to before, we were talking about software architecture, software design, as well as hardware architecture, and I'm going to talk about each of these concepts. We have graph analytical applications. We have the programming interface to the graph itself. We have a programming interface to the hardware itself. And then finally, we have the hardware architecture at the bottom driving all of it. The graph analytic applications we've talked about today. These are the things that you want to do. This is the mission. I want to route trains across a rail network across the US, or trucks across the highway system, or I want to look at editors on Wikipedia and understand their social networks. These are the applications that we want to solve. Again, we talked about malware distribution networks earlier today, BGP networks and computer networks. These are the hard problems that we have to solve that are represented by graphs. Graph programming interface. This is how the developer interacts with the graph. Again, I talked about an adjacency list. Programming graphs for an adjacency list is very different than programming for graphs in a matrix. So you end up using linear algebra and BLAS types of things. Then there's the hardware programming interface, which is what is the mechanism by which the developer can interact with the hardware? What is the software primitive that's presented to the developer? In these two examples, I have CUDA, which is NVIDIA's library for interacting with their GPUs. And I also have a high-level functional language, which we've been researching. And then finally, there's the hardware architecture. These are the devices that are running the programs. In our cases, we're looking at GPUs. We're building the software library, which rides on those two concepts, which is what is the interface to present to the developer for the graph, and which hardware programming interface we're going to use. Okay, so I've talked about graphs, I've talked about hardware, I've talked about the library. So we're not doing this alone. We have a strong collaborator in Andrew Lumsdaine at Indiana University. He's the director of the Center for Research in Extreme Scale Technologies, and he's well known in the graph community as one of the developers and the creators of the Boost graph library, which is kind of a standard library for interacting with graphs. And later he went on to do the Parallel Boost graph library as well, and so he's a strong collaborator. So I keep talking about graph analytics. Well, what do I mean by graph analytics? Well, just like the top 500 supercomputing list exists to measure how fast computers can do certain kinds of processing, there's also another benchmark called the Graph 500, which was inspired by the top 500. It was started in 2010, and it rates how fast computers and systems can traverse edges. And the standard algorithm that you use for graph traversal in this benchmark is the breadth-first search. And it's different than the top 500 because, again, doing graph processing is fundamentally different than doing other types of processing. You're not so interested in flops, you're interested in traversed edges per second. How many nodes and edges can I traverse per second to complete the whole graph? And Japan is currently in the #1 spot. Conveniently for us, on the executive committee of the Graph 500 is our strong collaborator, Andrew Lumsdaine. And so he helped set that up, and we work closely with him. All right, so I've presented the problem. Let's start talking about some results. Our early work was called Patterns and Practices for Future Architectures. And in this, we surveyed the literature to see what other people were doing in terms of graph analytics on GPUs. And we turned those algorithms that were published into code, running in our lab on our machines, running benchmarks. We fell in on the Graph 500 because that's an international benchmark. And we did it. And I'll show some of the results of that. All right, so all of you time travelers out there, last night we have a poster session that you can go see some of these charts and talk about some of our results. Okay, so on the bottom of this chart is a measure of complexity. It's lines of code, and we use a single CPU list implementation. It's a very simple graph traversal implementation as our baseline. It's our 1 times the amount of lines of code. And up on the y-axis is a log scale of performance of the traversed edges per second. And you can see that our standard there, our standard implementation, single CPU list, it's about 1 million edges per second. One CPU. Using a more complicated or more sophisticated algorithm and data representation, we can get an order of magnitude more performance out of the graph traversal with not much more code. That's a single CPU. It's called a compressed sparse row implementation. And then you see this big line. Oh, sorry. Going to the GPU. You can also see that with a little bit more code, you can get another order of magnitude on a single GPU. One GPU. One GPU. Using multiple CPUs and that linear algebra implementation, I can scale from 1 to 100 cores and get another order of magnitude scaling. This is interesting. Why are you messing around with GPUs if you can just do all of your stuff on CPUs? And the answer is this. I ran that on my $300,000 supercomputer, and I ran the GPU one on the $3,000 computer in my network. So the idea is to take this GPU implementation, reduce the complexity, and get even more performance out of it. We published this in a tech note earlier this year, and we were reached out to by Jeremy Kepner from Lincoln Lab, who was interested in this work, because last year the graph community had put out a position paper saying, enough's enough with all these adjacency lists and all these weird ways to represent graphs. Just do linear algebra, because everyone knows how to do linear algebra anyway. We've been doing it with BLAS for 30 years. We published these results, and we were actually invited to speak at HPEC, at the Birds of a Feather session for graph algorithms. They were really interested in this work. So more work we're doing with Indiana University is at that hardware programming interface, we're creating a lower level language for, well, a higher level language for working with lower level hardware. We're creating a functional language for doing GPU programming. And we were able to apply this to graphs as well. But you can see that our initial attempts have the same problems with traditional programming attempts doing graphs. They work on small graphs when you can fit it in memory, but they kind of slow down when you have bigger graphs. The second thing we're doing with the hardware programming interface is we're taking advantage of new features in CUDA. This is dynamic parallelism. So one of the challenges in doing GPU programming is the coordination between the CPU and the GPU, and a lot of work is done coordinating between those two. New version of CUDA has a feature where you don't have to do that. You can actually have GPU jobs launch more GPU jobs. And with that, we were able to make a breadth-first search implementation that beat other public implementations by 20 to 30%. It's interesting, by moving all of that work to the GPU, you can get rid of for loops. So it's kind of non-intuitive that when you're doing lots of work, you wouldn't want to use for loops. But if you're doing for loops, that means one entity is doing something, and then it's doing it again, and it's doing it again. I don't want to do that. I want 1,000 entities to go do something and give me the answer back, and then we're done. So some future work, more traversals. We're doing breadth first search, depth first search, shortest path, all the things that you heard about earlier today, things that people are doing for their mission. We're looking at that for our future work. And I want to call out one in particular, layout and visualization. It's really hard for a human to reason about 1 million things. So visualization is really, really important. That's all I have. Thank you.